floor is yours.
Thanks, Hans, and good afternoon, everyone, or good morning, or good evening, wherever you are in the world. I only have a few minutes. I really want to give Georg as much space as possible today to share in detail his research, which I think most of you will find very interesting. So I want to give a very brief introduction before I head over to Georg. And I would like the first slide, please. Thank you. No, second one. That's it. Yes, thank you. So our webinar is really quite timely. You know, just last week, you've probably all seen that the International Energy Agency, the IEA, published its landmark Net Zero 2050 report, and that made the headlines around the world. And one particular policy that was picked up by the journalists was the 2025 ban of fossil heating systems, which was part of the package of policies which the IEA put in their report. And this debate is still in full swing. So at least daily, I'm getting newspaper articles in the UK on this subject. And I'm sure in other countries, there's similar debate going on. So that it's a very timely discussion, I think, to have, given that we are, I think, at a point where things are really starting to pick up speed. Next slide, please. And again, same report here. The IEA is making some projections of what would be needed to meet net zero by 2050. And they believe by 2050, 55% of all heating systems used in buildings will be heat pumps, followed by solar thermal and district heating. And at the same time, of course, we will need to renovate existing buildings and also make sure new buildings are built up to a very high standard to ensure they are future-proof. So those are figures the IEA is projecting. There are many other projections, but I just wanted to share this particular projection with you to give you a flavor of what the scale of change could look like potentially. So what does the situation in Europe look like, which is where Georg's presentation will focus on today. Next slide, please. Thank you. So currently, and most of you should know this, and will probably know this, heating is quite carbon intensive in Europe. And a good comparison, I think, is to put this into perspective. All the emissions from heating just homes, not even all the other buildings that we have, is equivalent roughly to the emissions from all the existing coal power plants that are still operational in Europe. So it's a significant chunk of our emissions. And the climate neutrality goals set out in the European Green Deal really means that we will have to change that quite rapidly. And just recently, Frans Timmermans, the executive vice president of the Commission, who is in charge of the Green Deal, he reminded us last week of the scale of the challenge to meet net zero emission goals. And here's what the Commission thinks is needed. Next slide, please, Georg. Thank you. This is from the most recent impact assessment that looks at what kinds of policies might be required to meet the 55% reduction goals by 2030. And the numbers are really quite stark, I think. First of all, the Commission believes 60% emission reductions in buildings by 2030 based on 2015 levels will be required. And that's a very big reduction, unprecedented, will require a very big effort at all levels. And essentially what the Commission believes how this could be achieved is by two factors as laid out in the impact assessment. First, we will need to increase the energy savings rate by a factor of about 10 through renovating more buildings, increasing the depth of the renovations we undertake in terms of energy efficiency gains. That's a huge challenge. Currently, we are lagging far behind, both in terms of the renovation rate and the depth of the renovations that are undertaken. But the second step, and this is where I think the webinar today is particularly important, the second step is to accelerate the replacement rate of existing heating systems and install low carbon heating systems instead. And many of those are assumed to be heat pumps. So this gets me to the last and final slide before I hand over to Georg. So it is clear that converting fossil heating systems to heat pumps will result in significantly higher electricity consumption and additional load. There's no question about that. The degree, though, to which the existing power system can accommodate that additional load is a very important factor and has been hotly debated over many years, which I think is why Georg's presentation is particularly interesting. In the UK, and this is an example from the UK, this graphic made it onto the business cards of a well-known gas boiler manufacturer. And the picture on the right-hand side shows how gas demand in the UK exceeds current electricity demand several times in the winter months. And it has been argued that this shows that it will be extremely challenging to simply switch from gas to electricity. And I do agree with that. It is challenging. However, there are several factors that this argument ignores, and the graphic is too simplistic in my view. First, the actual peak gas demand is actually 40% lower, as more recent research shows. And second, if heat pumps are used, the energy required will be lower by a factor of about 2 to 3 because of the coefficient of performance, the high efficiency of heat pumps. And thirdly, if heat pumps were run smartly, and I know Georg will comment on this as well, the peaks could be reduced further, perhaps by as much as 30%. So let's get Georg to tell us what he thinks, how much space there is in the existing power system to accommodate heat pumps in Europe, in different member states. And in his work, he has looked at existing capacity and how much heat electrification would be possible at the moment without having to make further investments in capacity. So over to you, Georg. I'm looking forward to your much more technical presentation. Thank you.
Yes, thank you, Jan, for this nice introduction, and I will get right to it. So maybe let me start with the main findings of the study we conducted. It was published in a paper in the beginning of this year, and well, the first finding is, if we rely on heat pumps to decarbonize our heat system, member states can reduce their carbon footprint by up to 15% through electrification. So this does not go for all member states, as we will see later, but it depends on the heating in place at the moment. And this is without additionally expanding renewable electricity, so only with the system which we have at the moment with these emission factors. Then the second point is, all member states at the moment are far away from critical levels of heat pump deployment. And we have a large group of member states who has enough firm capacity readily available to reach even very far-reaching electrification degrees. And then the third point is 29 to 45% of EU space heating needs could be provided by heat pumps without overstressing the system we have today in place. And if heat pump deployment is in addition accompanied by additional renewable deployment, we could get rid of up to 16% of the EU's total annual emissions. So this does not concern the EU's heating emissions, but total emissions on the EU level. This is a brief overview over what will I be talking today. So first we'll start with a little look at what the current state of play with regard to heat pumps is in the European Union. Then I will give you a brief introduction on the method we applied, so how we generated the heat pump demand profiles, as well as what the electrification scenarios were, which we investigated, and then we will focus on the results. So if we look at the heating sector with regard to space heating across the EU, we can see that there is a very diverse picture. We have some countries in the north and in the east of the EU which have a large share of heating which is, as we can call, net zero ready, so which are technologies which go well with the goal of net zero. So we have either renewable-based heating, which is a lot of biomass, especially in Eastern Europe, but also district heating, which can be decarbonized through decarbonizing the heating grids, or electric-based heating, which can be decarbonized through decarbonizing the power system. And while this makes up over 90% in Sweden and up to 90% in Finland, for example, we see that especially in Central Europe and also Northwestern Europe, for example, Ireland, UK, Netherlands, Belgium, and Luxembourg, or Germany, we still have a very large share, more than 50% of fossil-based decentralized boilers, basically. So if we look at heat pumps, the big question is always, are they less carbon intensive than, for example, a gas boiler? Because the gas boiler is often the heating option, the non-renewable heating option with the lowest CO2 emission, or at least the fossil heating option with the lowest CO2 emissions. And if we compare the carbon footprint of 1 kilowatt hour of heat being produced by a heat pump with the footprint of one being produced by a gas boiler, we can say that in all these countries, which are boxed in red here, heat pumps are already more climate friendly than gas boilers. And even in those countries, for example, in Germany, in the Czech Republic, or in Bulgaria, where this is not yet the case, we can see that it's rapidly approaching the same level. So they are not far from parity in terms of CO2 emissions. So we can say that probably, even if we look now at all these countries, most countries, if we assume a lifetime of 15, 20 years, over the whole life cycle, a heat pump will be more climate friendly than a gas boiler. But if we look at the deployment rates, only 6 countries aim at market shares beyond 20%. So we just projected the last 5 years, which we had in our data sets, which goes up to 2015, and projected that into the future. And we see these countries, which are boxed in red, they reach shares beyond 20%. Others go more towards 5 to 10%. So not very high shares of electrification. And one aspect that we identified in our analysis, which plays an important role, although it's not the only, is the operating cost. So how much do I pay for 1 kilowatt hour of heat? And here we see that these countries which are projected to reach notable shares of heat pumps in their space heating system, basically, they often also have a cost advantage for heat pumps. So, for example, here we can see in France, there's a notable cost advantage, or in Sweden, even greater. The only exception to this, where heat pump heat is actually more expensive, is Belgium. So we see it's not the only factor, but it seems to be an important factor to speed up the deployment of heat pumps. This brings us to the method, which we applied for our analysis. And the first thing we did is we disaggregated the electricity demand from ENTSO-E into temperature dependent and non-temperature dependent demand, or even more specific, cooling degree hours and heating degree hours dependent. So we disaggregated it to have the part which is not sensitive to temperature, which can be seen here on the right side in green. Then the one that is related to heating in red, and the other part which is related to cooling in blue. And this method which we applied is based on heating degree hours. Many of you probably know heating degree days. So this is the same concept, just on an hourly level, not on a daily level. And then we applied a disaggregation model, which also took into consideration the coefficient of performance of heating and cooling technologies to give us a disaggregation of the demand, which is compliant with the national statistics on electricity demand. Then we created scenarios for heat electrification. So the first scenarios from EL20 to EL100, they describe a gradual electrification by replacing fossil heating technologies. So decentralized fossil boilers. For example, in the EL20 scenario, we take 20% of all fossil boilers and replace them with heat pumps. In the EL100, we replace all fossil boilers with heat pumps. Then we investigate additional scenarios. What if we also replace all biomass-based boilers, which we can see here in the EL100 bio scenario, and then in addition also district heating with heat pumps. So these, the last two scenarios, especially the last scenario, is probably not very realistic, but it can kind of serve as an upper bound to the discussion, because we will not get more electrification than if we build a heat pump basically in every building, if we supplied the entire space heating demand by heat pumps. And if we now want to know, okay, but towards which scenario are we actually aiming at the moment, we can see that most countries are aiming towards the EL20 scenario. So that means they're not even reaching this necessarily, but this is like the lowest scenario that they can get. And only a couple of countries reach for higher shares. For example, Belgium towards 40% and Greece. And on the other hand, Sweden is, even if this deployment rate that we see currently is maintained, and they even reach towards the EL100 bio scenario. So we will see if this slows down, whether they will also replace, for example, biomass with heat pumps. But this is the most ambitious electrification that we see at the moment within the EU. to give you a brief overview over the method that we applied, we took these demand curve that we constructed, and so one for each scenario, and then we analyzed based on the current firm capacities that we have in the EU. Does the demand exceed these capacities? So is there enough firm capacity to safeguard the demand increase we would see in these in each scenario? And this is, of course, a very conservative indicator. If we exceed the firm capacity, it does not mean necessarily that we will see load shedding, because we have still renewables. There might be free interconnector capacity, so that capacities from other countries can satisfy this demand. And so therefore, it does not mean load shedding. But if it is below the firm capacity, we can say that there will be no load shedding. So it's kind of like, it needs to be seen in this way. And then as a second part of our analysis, we wanted to know what is the impact on emissions. And for this, we also, for the first part, stayed very conservatively. We assumed that the additional demand from heat pumps is being satisfied by gas-fired power plants, because these are the ones, at least currently, with the ETS prices. Now this might change, but at the point when we did this analysis, the last plant in the merit order was usually a gas-fired power plant, and therefore we said the additional demand that comes from heat pumps would then be satisfied by a gas-fired power plant. And as a sensitivity, we also calculated how does this look like if we accompany heat pump deployment with additional renewable deployment. So if part of the electricity satisfying the heat pump demand is actually carbon neutral. So if we look at the number of hours which exceed the firm capacity, which can be seen in this table, we see that if we look at full electrification, so full replacement of fossil heating technologies, then there are still a lot of countries, I think 10 in total, which have no demand above the firm capacities, even if they replaced all these technologies. And we see there also is also a number of countries which have very low numbers. For example, 7 in the case of Czechia, 28 in the case of Croatia, and just as orientation, Finland already has 1,400 of these hours today. So it doesn't mean that in Finland, as I said, we have 1,400 hours of load shedding each year. This shows that Finland probably has a certain import dependence and relies on capacities in other countries. And if we, for example, take this as an orientation, we can see that actually most countries are below the level that Finland has at the moment already. So we can assume that the system is ready for far-reaching electrification. And to see how this changes further, if we employ load shifting, we assumed that the thermal inertia of the buildings can be used to shift the load. And if we employed this inertia based on some values we found from the literature, which said basically per 1 square meter you can shift 0.1 kilowatt hours, if you assume that the inhabitants are fine with a deviation of 0.5 degrees Celsius, then you get that roughly you can shift 6% of peak demand to off-peak hours. And if we employ this now and look at our table again, we see that the number of hours above the firm capacities goes even further down. So then we have 12 countries instead of 10, which have 0 hours above the firm capacity in the EL 100 scenario. Then one might, of course, ask, okay, this is the case now, but for example, in Germany, we are planning to phase out nuclear. A lot of countries in the EU, they're planning to phase out coal or are already on track to do so. How does this look like in the future? And here we took the Potentia Central scenarios, so from the Joint Research Center of the European Commission, and took the annual capacity levels to basically look how much demand is above the firm capacities. And for orientation, it starts a little above 2%. So what we just saw in the last two tables is roughly 2% or a bit more. And here we can see up until 2030, the situation does not really change. So we are starting maybe a little bit at above 2%, and in 2030 2030, it's roughly 3%. In the longer run, however, there might be a different situation because more capacity exits, there are more renewables and there are less reliable capacity. So in the longer run, we might we might have to monitor the situation because there it's actually not so sure. But also this means there is still time to react. So if we see, for example, that the necessary investments are not being realized, it's not the day after tomorrow, but it's after 2030 where the situation might become a bit more critical. So this brings us to the impact on emissions. And this table shows you basically the change in total national emissions. So also not to, with regard to the heat sector, but on a total national level. And here we can see that if we only replace fossil boilers, even if the additional electricity is generated by gas-fired power plants, which is the basis of this this table, then up to the EL100 scenario, everyone is reducing emissions. So with the until then, if you only replace fossil boilers, it always leads to an emissions benefit, even if the electricity is generated by gas-fired power plants. If we move on then and replace also biomass or district heating, then the picture is a bit more diverse. For example, in Lithuania and Latvia, we see that the emissions actually increase. This is because they have large district heating systems, they have a lot of biomass in the system, and so if these get replaced, then the emissions increase. In the case of Poland, for example, we see that there is still a large emissions benefit if we also would replace district heating with heat pumps, because district heating in Poland is predominantly provided by gas-fired plants. This brings us to the sensitivity in terms of how the electricity is provided that fuels the heat pumps, basically. And here we see if we are going towards further degrees of electrification. So this is the curve for the EL20 scenario. This is the curve for the EL100 all scenario. Then it becomes more and more important that the electricity is being provided by carbon neutral sources. And if we do so, if we couple heat pump deployment with electrification through heat pumps, we can save up to 16% of the EU's total emissions, which is kind of this point here in the end. This doesn't necessarily need to increase the cost of the system, because I mean, the LCOE of wind is somewhere in the range of 40-50 euros per megawatt hour, and this is also the marginal cost of a combined cycle gas turbine. But of course, if we then get to a point where additional wind power a lot of it is curtailed, then this is not fitting the analysis anymore, because then the LCOE of additional wind power could actually increase again. So how much heat pumps could we install in the European system based on today's capacity? And if we assume, this is what we did here on the right, in each country we picked the scenario which can be safeguarded by the current capacities, which you can see it's between only the current system in Austria and Belgium, or even the EL100 all scenario in Bulgaria. Then we took the amount of heat pumps we would apply in each scenario, we add this up, we get a number of 1.1 terawatt hours of heat pump capacity that you could install across the EU, which is of course massive. I would not necessarily say that it would be assigned like in these scenarios, but of course, since we have interconnectors, it could also be deployed more distributed across all member states. And if we even assume a flexible dispatch of heat pumps, which is on the right side, the demand response scenarios, we can even install 1.6 terawatt across the European Union. So this is still far away from what we see at the moment, the deployment. But if we did so based on the current electricity system, and also assuming that gas-fired power plants provide the additional demand, so with no additional renewables, we could save 116 to 169 megatons CO2 annually, and this corresponds to 3.4 to 4.9% of the EU's total emissions. So just based on today's power plant park. So that brings me to my key takeaways. So if fossil boilers are replaced, heat pumps lead to an emissions reduction in all EU member states. And on a national level, we can reduce up to 15% of total emissions, of total national emissions through electrification, even if we do not accompany this by additional deployment of renewables. And currently, all member states are far away from critical levels of heat pump deployment based on current deployment rates. A majority of member states also has enough firm capacities readily available even for far-reaching electrification. But there are some member states, which we also saw in our analysis, which should be aware of heat pump deployment and monitor whether the necessary investments in the power sector materialize to safeguard the additional demand. In total, we concluded that you could deploy 1.1 and 1.6 terawatts of heat pump capacity across the EU, depending on how flexible heat pumps operate, without overstressing the system that we have in place at the moment. And this would correspond to 29%, to between 29 and 45% of the EU's space heating needs, and reduce carbon emissions by 3.5 to 4.9%. And the larger level of electrification, the bigger is the impact of the electricity mix. If we combine heat pump deployment with simultaneous expansion of renewable capacities, then we could save up to 16% of the EU's total emissions. Yeah, thank you very much.